would like to talk about the anatomy of transfer functions. Okay, so up to now we have done these three standard systems, right? And we've approached them not from a general mathematical point of view, but rather from a example-driven kind of point of view, saying, well, if I have a tank and I do the differential equations, so if I have one tank, if I have my classic tank example over here, I know that that is going to be something like this. Actually, if I have another kind of tank, which is, I'm indicating a pump there to indicate a constant outflow. In that case, I have an integrating system. And if I have two tanks in series, I have a second order system. Now, we spoke about the step responses of these systems within the context of actually understanding what those systems would actually behave like mechanically or physically. In the case of a first order, we've got that k-tau box. In the case of an integrator, now again, these things that I'm drawing are unit step responses. Okay, so in other words, I'm introducing a unit step here. In the case of the integrating system, that goes on and on forever at a slope of k. And in the case of the second order system, now I'm going to do two. In the case of the kind of system that's drawn here, the tanks in series kind of thing, that's first orders in series. And you can put as many of these first orders in series as you'd like, and you will simply see slower and slower responses with higher and higher orders of continuity in their step response. So we assume all of these responses have been zero until the thing happened, right? So until we saw the change, they were zero all the time, and then they started changing in response to the signal, or in response to the input at time zero, right? And so notice that all of these responses are continuous even though the input is discontinuous, but we can see that the first two, the ones that have only one S in the denominator, show a discontinuity in their first derivative. And so we would describe those as continuous functions with discontinuous first derivatives, or first order smooth functions. Okay? Here, this function has a continuous first derivative but a discontinuous second derivative, and so that would be second order smooth, right? In general, if we have 1,000 tanks in series, they'll exhibit 1,000 order smooth responses. So you could take that many derivatives and still have a continuous function. And what that translates to in what it looks like is that this lag over here becomes more and more gradual, right? So you see this very gradual kind of change in the slope, where here you've got this instantaneous change in slope. Here you've got a gradual change in slope. Now, obviously, the general second order system, what I've drawn there is the response of an overdamped or critically damped system, because it only goes up exponentially, or it kind of asymptotically approaches that system. There's a generalization of this, which we recognized yesterday when we just substituted that zeta in there. And we just played around with the math. We saw that for small zeta values, the response got qualitatively different. In other words, it started doing this kind of thing, right? And so this is for zeta greater than 1, and this is for zeta between 0 and 1. Now, just remember that we've spoken about this difference that even though this is the caricature version of the second order underdamped response, this overshoot and oscillation, that's only really visible for zetas kind of less than about 0.7 rather than less than 1. So this is really quite a pronounced, very small underdamped response. Also, it's possibly also useful to imagine what kind of liquid system would exhibit this kind of oscillatory behavior. And one place where we see something similar to this is when we have two tanks that are connected in this way, where flow can be introduced into either one of these tanks. And so what will happen in this case is if there's a large flow, if there's a large flow, the flow will start pushing into this direction, and you can actually get this oscillatory behavior in this U tube. So this is what an underdamped system would look like, where the levels would be oscillating like this. Now, let's talk about what these different transfer functions actually look like. Let's talk about what these different transfer functions actually look like. I've summarized the three common forms that are used for describing transfer functions here, and these are also a little bit related to the way that they're represented on computer systems. So in the one case, we have what is known as the zero pole gain case. Now, I've written the gain over here, but technically this system would be completely specified if we just specified all the poles in zeros. But we probably want to be able to specify the overall gain separately, as the gain is a very important property of the transfer function to have. In this form, we've factored out the numerator and denominator polynomials. And what's important to understand about this form is that it is not always going to be possible or reasonable to factor this form out with real numbers over here, as we saw over here. If zeta is between 0 and 1 for this standard second order system, it is actually not possible to factor that with real roots. We actually have complex roots. So when we write this form, it's not necessarily always going to be pretty. This is written in such a way so that we can effectively define these two properties. The zeros of the denominator, in other words, the places where, or the roots of the denominator, the places where the denominator becomes 0, are known as the poles. That's why I've used a P over here. And the roots of the numerator are known as zeros, which is why I've used Z over here. And you should be able to verify easily that because I've factored this out, whenever any one of these parentheses or these terms becomes 0, the whole numerator or the whole denominator becomes 0. So when S is equal to Z1, or when S is equal to Z2, or when S is equal to Z3, and so on, then G of S, or G of Z1, right, would be equal to 0. And similarly, if S becomes equal to P1, P2, or P3, then I'm dividing by 0, and I end up with a singularity. Now, the other form that we've got, which is quite standard, is the time constant form. This is typically only used when the time constants are real. So we have similar concerns as we had with the previous form, where it's not always possible to factor the polynomials in such a way so that these coefficients are real. As we saw earlier, in many cases, the behavior, the higher order behavior, actually arrives from having first order systems in series. And in that case, it is possible to just have these effectively pre-factored. We just don't multiply them out. We just have all of these terms one after the other. Then, of course, in the expanded form, we have just polynomials, and a widely used standard is to have the highest order of S at the front, going all the way to the lowest order of S. This will be a constant, so S to the 0 is obviously equal to 1, and so we'll just have B0 and A0 there. This is the form that is favored by computer software, and typically many of these computer softwares will allow you to just enter these coefficients, a list of coefficients for the numerator and a list of coefficients for the denominator in order to define g of s. So those are the parts. So let's just run through them again. So we have the numerator, we have the denominator, we have these things are called zeros, these things are called poles, these things are called time constants, and these things are called coefficients. And each one of these forms is typically convertible between, so you could start with a form like this, and if you just multiply everything out, you'll end up with the expanded form, or if you have a form like this and you multiply everything out, you get the expanded form. In order to get from the expanded form back to one of these factored versions, you have to calculate the roots of the numerator and the roots of the denominator, because in general, commands that would factor the polynomial wouldn't end up with the full set, simply because most of those commands will try to factor with real coefficients.